Hi everyone, welcome to the fourth lecture of this fourth module where we are discussing interface circuit for microsensors and nanosensors. Today we are going to learn about ratiometric circuits and some bridge configuration. Okay. So, to improve the accuracy of a sensor, ratiometric technique is a powerful method. Okay. This is useful when the error source has multiplicative nature, but this kind of circuit is not useful when the error source has additive nature. Okay. So, this kind of technique is actually useless for reducing thermal noise because of its additive nature. Okay. However, this kind of technique is very useful for places where you have power supply variation, where you have lot of variation because of ambient condition like variation in temperature, humidity or pressure condition. In fact, this kind of circuit can also be helpful for neutralizing or at least minimizing the effect of edging which is coming from the say receptor material or a transducer in a sensor. The idea behind this kind of technique is to use two sensors of which one is a acting sensor, and acting sensor responds to external stimulus, while there is another sensor which we call a compensating sensor or a reference sensor. So, compensating sensor is either shielded from the stimulus or it is actually insensitive to any variation. Okay. So, both sensors must be exposed to all other external effects which may be multiplicatively changing their performance. Okay. So, a ratiometric technique essentially require the use of division. It can be performed by two standard methods, one for digital and another for analog. In a digital form, the output signals from both the acting and reference sensors are actually multiplexed and converted into binary codes by using some AD converters. Okay. Subsequently, you use a microprocessor to perform the operation of division. So, basically the ultimate idea is to do division. Okay. Now, let us see this for analog condition because that is what we are going to use most of the time. In an analog form, a divider may be used as a part of signal conditioning circuit. Okay. So, a divider produces a voltage or current which is proportional to the ratio of the two input voltage or current. So, this is a divider, for example. Okay. I have two input V1 and V2. V1 is coming from acting sensor and V2 is coming from the compensating sensor. Right. So, this divider takes care of the division, okay, and V0 is directly proportional to V1 by V2, and to remove this proportionality I have introduced a constant. So, this is K V1 by V2. So, when V1 and V2 are equal, actually the output voltage is nothing but the constant value. Okay. The simplest ratiometric circuit without any amplification condition is a voltage divider circuit. Okay. So, the most basic electronic interface circuit for a resistance based sensor uses this kind of voltage divider circuit to convert the resistance to voltage. Okay. In this configuration, say this RS is the sensor's resistance while this is the load resistance. Okay. The output can be given as RS by RL plus RS into the supply voltage. Okay. While the simplicity of this circuit is very appealing, I mean you can utilize or anyone can design this circuit. However, the output voltage of the circuit is basically non-linear function of the sensor's resistance, and we know what are the effects of non-linearity of a sensor. Okay. So, when your sensor this RS is non-linear in nature, this actually reduces the sensor resolution. Okay. As the sensor's resistance varies from the load resistance and limiting the use of dynamic range of the circuit. Even the dynamic range of the circuit is very large. However, because of this sensor's non-linearity, you cannot use the complete range. Okay. For resistive sensor with the high baseline value, the input resistance of the subsequent interface circuit must also be high to avoid any load related error. We have seen that when we have seen the input and output impedance characteristic of a sensor while discussing in module 2. Okay. So, I mean how to avoid these things and how to overcome the non-linearity factor of the sensor, although we have to use some ratiometric kind of condition so that we are improving the accuracy of the sensor through interface circuit. Okay, so Wheatstone bridge kind of configuration is very useful in such condition. Okay, so a Wheatstone bridge circuit can be used to reduce the influence of baseline resistance on the ultimate dynamic range of the interface circuit. Okay, and we have discussed that what is the baseline resistance of a sensor. Say for example, if I have a chemiresistive device, the same example that we are taking since module 1, okay, I have, say, there is a change in, say, the initial resistance with, say, certain voltage bias at, say, 1 volt, okay, initial resistance is R, okay, and when it is exposed to some analyte, in presence of analyte, this resistance is RA, okay. So when there was no analyte, or when this analyte was 0, okay, the resistance of this device is known as baseline resistance, right? And when this sensor is exposed to analyte, the resistance changes to RA value, okay. Of course, we have to quantify the difference between R and RA, and then we have to normalize, and then there are other procedures to calculate response and other parameters. But I have given this example to understand the baseline resistance. So a Wheatstone bridge circuit can be used to reduce the influence of the baseline resistance on the ultimate dynamic range of the interface circuit. Okay, they are very popular and effective implementation of the ratiometric techniques. Okay. Now let us consider a Wheatstone bridge. I mean, this is a basic configuration of Wheatstone bridge. You can see that there are 4 arms, R1, R2, R3 and R4. Usually this, you are taking this voltage output for the current scenario, but usually this bridges works on null deflection, where this portion is connected through a galvanometer, where usually we keep the galvanometer at 0 current, or this is basically a null detection type of instrument. We will see this Wheatstone bridge circuit in little bit more detail. Okay. So at the baseline condition, when the sensor's resistance, this Rs, is equal to the baseline resistance R, the output of the Wheatstone bridge is configured so that the output voltage V0 plus minus V0 negative is 0. Okay, as I have just mentioned that this is a null kind of instrument, so, or null kind of circuit. So usually we have to manage it in such a way by changing R2, R1 or R3 or any one of it, okay, so that this bridge is in balance condition, or this voltage is 0. Okay. Now there are 3 variations of the basic Wheatstone bridge circuit for measuring resistance. Okay, particularly we are discussing for resistive kind of sensor. Okay, you have a single element configuration, then you have a dual element configuration, and you can also have a 4 element configuration. Okay, let us see all these 3 configuration in brief, and then we will move ahead in Wheatstone bridge. Okay, let us see a single element Wheatstone bridge. This is a single element Wheatstone bridge configuration. The circuit is configured such that R1, R2 and R3 are all set equal to R value. Okay, which is the baseline resistance of the circuit, okay, of the sensor. So R1 is equal to R, similarly R2 is equal to R, and R3 also is equal to R, while the sensor's resistance was, the baseline resistance was already at R. Okay, as I have mentioned, the R is the baseline resistance of the sensor. Now the total sensor resistance is for any kind of variation is R plus delta R, where the delta R is the change in resistance because of external stimuli which I am trying to measure using this resistance. Okay, so the output voltage of the circuit in that condition will be delta R by 4 into VDD, which is this voltage, into 1 by R plus del R by 2. Okay, by this I can calculate this output voltage. So by this mean, if you see, what I am doing is I am doing the change in this resistance. Okay, this reflection of this is being seen in the output voltage. All right. So there is a change in resistance, and I am able to convert that change in terms of some voltage. Okay. Of course, this voltage has to be fed into another interface circuit element, maybe say ADC or some other thing. Okay. Now let us see a dual element Wheatstone bridge configuration. So if more gain is desired and it is possible to manufacture two nearly identical sensor of resistance Rs. Okay. So in this condition you need two very similar sensors. So you have one sensor Rs, you need another sensor having the same resistance. Okay. Or you want, particularly this is very helpful for batch fabrication where you have multiple sensors of equal resistances. Okay. So a dual Wheatstone bridge provide twice the gain that is of a single element version. Okay. Now what I will do is in this case R1 is also basically not a resistance but also a sensor. So you replace this R1 with a sensor resistance Rs. Okay. R2 and R3 are set to equal to R, which is the baseline resistance of the single element version. Okay. Now in that case, when this is sensor's resistance, this is another sensor having same resistance Rs, okay, and R2 and R3 are having a value equal to R. In such a condition, this V out will be equal to delta R by 2 into VDD into 1 by R plus del R by 2. If you remember, in the single element Wheatstone bridge configuration, this was delta R by 4. Okay. So basically what you are doing is you are improving the gain by 2 times. Okay. The dual element circuit reduces the influence of the baseline resistance on the output voltage, very similar to the single element Wheatstone bridge, but it is still vulnerable to changes in the power supply because in this term you are having a VDD term. Okay. And produces an output voltage that is a non-linear function of the input resistance Rs or the baseline resistance R. Okay. Now let us see another configuration which is known as 4-element Wheatstone bridge circuit. Okay. In this case, it is possible to orient sensors such that some exhibit an increase in resistance equal to R in response to a stimulus, while others will exhibit an identical decrease in the resistance. In the 4-element configuration, this R1 is equal to R plus delta del R. This is also equal to the sensor's resistance Rs, while R2 and R3 are manufactured in such a way or placed in such a way that it represent the R minus del R value. Okay. Del R is the change in resistance. In such a case, V out is equal to del R by R into VDD. So a 4-element Wheatstone bridge provides an output voltage that is a linear function of the sensor input. However, if you see, it is still a function of VDD. Okay. Like other Wheatstone bridge configuration, it drastically reduces the influence of the baseline resistance. Okay. Wheatstone bridge circuits are widely used and highly effective for implementing the ratiometric or division technique at the sensor level. And this is the basic configuration of Wheatstone bridge with a galvanometer connection. Okay. Just have a look on this configuration. Okay. Now the output voltage of this kind of circuit is equal to, say, if I am considering this Z1, Z2, Z3, Z4 as impedances in the 4 branches. Now I am going little beyond than the resistive sensors. Okay. The output can be given as Z1 by Z1 plus Z2 minus Z3 by Z3 plus Z4 into reference voltage, where this is the reference voltage. Okay. Now this bridge is considered to be balanced when this V out is 0. Okay. When this V out is 0, basically this Z1 by Z1 plus Z2 is equal to Z3 by Z3 plus Z4, and if you equate it, actually you will achieve a condition where Z1 by Z2 is equal to Z3 by Z4. Okay. Under the balance condition, actually the output voltage is 0. Okay. When at least one impedance in the bridge changes, the bridge become imbalanced in nature. Okay. the output voltage goes either in a positive or in a negative direction depending on the direction of the impedance change. Okay. So to determine the bridge sensitivity with respect to each impedance, which is also known as calibration constant, partial derivative can be obtained from the output equation. So if you say I am calling this equation 1, if you differentiate this equation with respect to Z1, you get the sensitivity with respect to say Z1. Okay. So if you differentiate it, the partial differentiation will give you Z2 by Z1 plus Z2 whole square into V reference. Okay. Similarly, you can achieve this for other, with respect to other impedance also, like D. For Z2, we have dV out by dZ2 equal to minus Z1 by Z1 plus Z2 whole square into V reference. Okay. If you do it with respect to Z3, you get dV out by dZ3 equal to minus Z4 by Z3 plus Z4 whole square into V reference. Okay. Similarly, for Z4, you get dV out by dZ4 equal to Z3 by Z3 plus Z4 whole square into the reference voltage. Okay. These are known as calibration constant of a Wheatstone bridge. Okay. So if you sum all these, you get actually the bridge sensitivity. Okay. So if you do the summation, you get del V out by V reference is equal to Z2 into del Z1 minus Z1 into del Z1 divided by Z1 plus Z2 whole square minus Z4 into del Z3 minus Z3 into del Z4 divided by Z3 plus Z4 ka whole square. Now, please note that the impedances in the balanced bridge do not have to be equal as long as it satisfy the equation Z1 by Z2 equal to Z3 by Z4, because this is the condition where the Wheatstone bridge achieves the null condition. Okay. Now, recall our first case where only one impedance has been used as a sensor. Therefore, for Z1 as a sensor, the bridge sensitivity is nothing but dV out by dZ1 equal to Z2 by Z1 plus Z2 whole square into reference voltage, or dV out by V reference can be written as dZ1 by 4Z1. Okay. So if you know the change in impedance for your sensor, right now I am telling that only Z1 is my sensor. In that condition, the bridge sensitivity, please note that I am not talking now sensitivity of one arm, I am talking about the bridge sensitivity overall. It is dV out by V reference equal to change in the impedance of the sensor divided by 4 into the impedance of the sensor. Okay. Please note that these resistive bridge circuits are very common in various sensors, including strain sensors. You will see most of the strain gauges or micro strain sensors configured as a bridge condition, okay, or in a Wheatstone bridge. Similarly, piezoresistive pressure transducers are comes like this. Okay. Similarly, thermistor, hygrostor and other sensors you will find having this kind of bridge configuration. Okay. Apart from this, capacitive and magnetic sensors also use a similar arrangement to measure various non-electrical parameters like force, displacement and moisture. We have not discussed any of them now, but in the next module, of course, we are going to discuss all of them. Okay. Now, to measure using this Wheatstone bridge, there are two methods depending on how to disbalance this bridge, or you can say vice versa, how to balance the bridge. Okay. You have seen that in the Wheatstone bridge configuration, you have usually in the balance condition, the galvanometer shows zero current or there is no current. So you can do the measurement by achieving this null balance. Okay. Or there is another way that if null balance is already there, you can disbalance this by changing some of the parameter, and if you can measure that, okay, that what is the effect on its null condition, you can actually measure that particular instance. Okay. So therefore, I can say that there are two different methods for measurement using a Wheatstone bridge configuration, that is known as disbalance bridge and null condition, okay, null balance bridge. Okay, so we'll see them one by one. I am giving one example of disbalance bridge condition. Okay, you can see that Wheatstone bridge in the disbalance bridge measurement condition is shown over here. Okay, you have R1, R2, R3 and this RV as the sensor present in this circuit. Okay, so a basic Wheatstone bridge circuit normally we know that operates with a disbalance bridge. Okay, this condition is known as, or this method of measurement is known as deflection method of measurement. Okay, so it is based on variation of the voltage across the bridge diagonals. Okay, so the bridge output voltage is a non-linear function of disbalance, say delta, with the sensor's resistance RV. I am calling it R plus R into delta, or R into 1 plus delta, where delta is the disbalance. Okay, for a smaller change where delta is very small, say even less than 0.05, the bridge output may be considered as a quasi-linear. Okay, in that condition, bridge sensitivity is maximum when R1 is equal to R2 and R3 is equal to R, right? When R1 is much larger than R2 or R2 is much larger than R1, in that condition bridge output voltages decreases, and say consider that this constant K is R1 by R2. Okay, the bridge sensitivity can be written as V by R, or simply K by K plus 1 whole square. Okay, this is the sensitivity of the bridge. By this method, you can actually measure, dynamic changes in the input. Okay, however, with the null balance condition, mostly it is used for static changes, but this method is also very, very effective. So it overcomes the limitation of small changes. You have seen that I can do the measurement where this delta is smaller than 0.05. Okay, however, this null condition overcomes the limitation of small changes in delta and it achieves a good linearity. Here, the bridge is always maintained at the balance state, and this requirement of bridge balance is satisfied by varying another arm of the bridge along the sensing arm. So what is happening is, my sensor is introducing some changes in the circuit. Okay, now I have a control circuit through which I am able to change the resistance in another resistance. Okay, so the control circuit modifies the value of, say here R3, but it can also be connected to any other resistance. But then you have to mind that if I am changing R1, there will be disruption in R2 also. Okay, so you have to use the control circuit very carefully. Okay, the control circuit here modifies the value of R3 based on the signal from this error amplifier. Okay, so what is happening is there is a changes in or disruption in this sensor. Okay, because of that this circuit is going imbalance. Now I am changing this R3 through the input from this control circuit, which is taking output from this error amplifier in such a way that I am achieving the null condition. Okay, the sensor's output voltage can be obtained from the control signal of the balancing arm R3. Okay, this can be understood with the example of photoresistors. Okay, say consider RV and R3 are phototransistors. The sensor and this resistor R3 both are photoresistors. Okay, now R3 is a photoresistor which is interfacing with a LED which is controlled by a error amplifier. Okay, now the resistance RV, which is my sensor, and the light having RV as a resistance, and the light intensity detected by the sensor can be determined by the current through the LED, which is controlled by the error amplifier. So in turn, actually the output from this photoresistor is changing, and R3 and RV are syncing with each other in such a way that I am achieving this null condition, and by that I am able to measure this. Okay, now this is how we measure using a bridge condition or Wheatstone bridge. Okay, but using, apart from this measurement, this bridge amplifiers are also very popular. In fact, the bridge amplifiers for resistive sensors are probably the most used sensor interface circuit that exist. Okay, So, bridge amplifier will not be able to cover in detail, but I will show you some basic configuration of a bridge amplifier. Okay, this bridge amplifier exists in various configuration that depends on the required bridging grounding and availability of either grounded or floating reference voltages. Okay, this is one of the configuration. In this figure, an active bridge is shown over and a variable resistor, which is this Rx, is floating and is connected into a feedback of this op-amp. Okay. When I say floating, actually I mean to say that it is isolated from the ground. Okay. Now, the first order resistive sensors transfer function can be modeled as Rx is equal to R naught into 1 plus alpha, where alpha is the, say, input stimulus. Okay. Now, the transfer function of this kind of circuit is very simple. This V out can be written as V by 2 into alpha V by 2, where alpha is, again I have mentioned that, is the input stimulus. Okay. I mean, this is a very simple bridge amplifier configuration. Okay. There can be other configuration also, like you can see here, a circuit with a floating bridge and floating reference voltage is shown. Here both are floating. Okay. The output voltage in such a case is a little bit complicated, and in such condition where this NR is the feedback resistance, the output voltage is written as V by 2 plus 1 plus N into alpha, where alpha is again the input stimulus, into V by 4 into 1 by 1 plus alpha by 2, or it can also be given as V by 2 into 1 plus N into alpha by 2. Okay. In figure, a bridge with asymmetrical resistor where R is not equal to R naught with a floating reference voltage source V is shown. Okay. In this condition, the output voltage can be written as V by 2 plus N into alpha into V by 4 into 1 by 1 plus alpha by 2, or V by 2 into 1 plus N alpha by 2. Okay. Then there is another configuration of bridge amplifier. I mean, there are number of configurations that exist. I have given only 3 examples. Here there is in this figure, a resistive sensor is grounded. Okay. And its interface circuit has a desirable gain. And the output voltage can be given as V by 2 minus N by 2 into V by 1 plus 1 by 2N into alpha by 1 plus alpha, which is also equal to V by 2 into 1 minus N by 1 plus 2N into alpha. Okay. So, these bridges are very important in designing the bridge amplifiers, which I have just mentioned that it is the very useful amplifier circuit, particularly for resistive devices. Okay. So, with this we have discussed some ratiometric technique and bridge configurations for measurement as well as for amplification. Okay. We will again meet in the next lecture with some more discussion on the interface circuit, and then we will wrap up this module. Thank you.